In 2001, Nikon reigned as a shogun of chipmaking, commanding about 40% of the global lithography market. Its steppers printed the circuits in countless silicon wafers. But fast forward to today, and that dominance has all but evaporated. Nikon's share has dwindled to roughly 7%. How did a titan of the 1990s fall so far behind? It's as if the once mighty shogun was dethroned overnight by a European upstart. In fact, one Dutch company, ASML, now controls over 60% of this critical market and has a 100% monopoly in the most advanced extreme ultraviolet EUV tools. Consider this stark contrast. ASML's EUV lithography machine costs more than $150 million apiece and guzzles enough power to light a small neighborhood. Yet chipmakers line up to buy them because EUV is the key to cutting-edge processors. Meanwhile, Nikon, the former champion, sold exactly one experimental EUV tool back in 2008, and then fell silent for years. By 2017, Nikon's high-end lithography business had retrenched so much that ASML held over 90% of the immersion lithography market too. It seemed like game over. But this story isn't over. In 2025, Nikon is quietly mounting a comeback, not by directly attacking ASML's EUV stronghold, but through a flanking maneuver. The Japanese icon is betting on two overlooked frontiers in chip manufacturing: advanced chiplet packaging and nanoimprint lithography. These are areas where ASML isn't as entrenched, and where Nikon's precision engineering might just shine again. It's a bold play, akin to a master strategist avoiding the enemy's fortress and targeting the unguarded flanks instead. Can Nikon really come back? The answer lies in understanding how this once dominant player fell, and how it plans to rise again by rewriting the rules of the war. What's EUV? In chip manufacturing, lithography is the process of printing tiny circuit patterns onto silicon wafers using light. Deep ultraviolet, DUV, lithography, using 248 nanometers or 193 nanometers light, was the workhorse technology for decades. It's still widely used for chips in cars, IoT devices, and everyday electronics, with tools from Nikon, Canon, and ASML serving nodes in the 28 to 90 nanometer range. But to push transistor sizes smaller, 7 nanometers and below, the industry turned to extreme ultraviolet, EUV lithography, around 2018. EUV uses 13.5 nanometers wavelength light, requiring exotic lasers and vacuum systems to etch incredibly fine features. EUV has become the gold standard for the most advanced logic chips. ASML is the only company that produces EUV machines at scale, and each one can cost $150 million to more than $350 million. These massive tools enabled the continuation of Moore's law by packing billions of transistors onto a sliver of silicon. The global semiconductor landscape today is heavily shaped by EUV. ASML's EUV tools are used by TSMC, Samsung, and Intel to make our fastest processors. Nikon and Canon, once dominant, now mainly supply DUV machines for older nodes and specialty markets. It's a bit like a technology leapfrog. Nikon perfected the older generation, but ASML leapfrogged ahead with a risky new technology and now reaps the rewards. The world's thirst for advanced chips, for smartphones, data centers, AI accelerators, made EUV indispensable. That's why ASML's stock has soared in recent years. Now, what about this dark horse called nanoimprint lithography? Traditional lithography, DUV or EUV projects, circuit patterns through lenses onto the wafer using light. Think of it like a projector casting an image. Nanoimprint lithography, by contrast, works like a stamp or mold. Instead of shining light, NIL presses a template with nanoscale circuit patterns directly onto the resist-coated wafer. It physically imprints the pattern in a single step, potentially even creating 3D structures in one go. The concept has been around for years in labs, but only recently have companies like Canon begun to turn it into a manufacturing tool. NIL promises a radically different approach. No expensive lasers, no giant lenses, no vacuum EUV light source. That could mean dramatically lower costs and energy use, if it can be made to work in high-volume chip production. Why Nikon's new strategy matters now, The semiconductor industry is at an inflection point. The cost and complexity of pushing further with EUV are skyrocketing. The next-gen high-NA EUV machines will exceed $300 million each. At the same time, more approaches are gaining steam. Instead of making one monolithic chip ever smaller, companies are looking at chiplets and advanced packaging to keep improving performance. By combining multiple chips in one package, like a tiny circuit board, they can mix and match technologies and boost yields. Artificial intelligence, AI, and the Internet of Things, IoT, are driving an explosion in demand for high-performance chips, which in turn pushes innovation in how those chips are put together. Advanced packaging, including techniques like 3D stacking and chiplet integration, is becoming as critical as lithography itself for cutting-edge systems. This is the arena Nikon is targeting. And with geopolitical shifts, e.g. countries wanting more domestic chip capability, there's appetite for alternatives to the ASML-centric status quo. Nikon's pivot to packaging and NIL comes at a moment when the industry is more open to different solutions, not to replace EUV outright, but to complement or work around it. In short, Nikon's flanking attack is timely because it aligns with where the chip world is headed: heterogeneous integration and cost-effective manufacturing. Before we dive into Nikon's master plan, let's recap how the fall of the Shogun happened, how Nikon went from top dog to underdog in the span of 2 decades. In the 1980s and 1990s, Nikon, along with fellow Japanese firm Canon, was on top of the semiconductor world. To put it in perspective, Japanese companies controlled about 70% of the global lithography market in 1989. Nikon's steppers were considered state-of-the-art, churning out the microchips that powered the early PC era. The company's precision optics legacy, honed from its camera business, translated into superb lithography lenses. By the late 90s, if you were building a fab, chances were good you'd be buying Nikon or Canon machines. They were the shoguns of lithography, ruling an empire of silicon. Yet, in the background, a small Dutch competitor was steadily rising. ASML, once a partnership between Philips and the Dutch government, had entered the race in the 1980s. At first, ASML was a laggard. Nikon and Canon had the bigger market shares and more experience. But ASML had a penchant for betting on unproven ideas and pulling in partners. In the mid-1990s, ASML set its sights on a crazy concept being discussed in research circles: extreme ultraviolet lithography. Nikon and Canon were aware of EUV as well, but regarded it as too risky and far off. Instead, in the late 90s, Nikon doubled down on perfecting DUV, for example, transitioning from dry to immersion lithography with water between the lens and wafer to improve resolution. Nikon's strategy was to keep improving the existing 193 nanometer technology. It was a conservative approach, sensible at the time, but it turned out to be a fateful misjudgment of the technology route. ASML, by contrast, took a gamble and integrated global technology resources to pursue EUV aggressively. The turning point came in the early 2000s. In 2002, ASML's sales surged and its market share leapt above 50%, overtaking Nikon for the first time. In just 1 year, Nikon's lithography revenue plummeted by half, from $1.49 billion in 2001 to $773 million in 2002. This was the moment the shogun lost his throne. ASML had won over key customers like Intel, IBM, TI, and TSMC by offering cutting-edge tools and a bold roadmap. Nikon, meanwhile, saw its share fall from approximately 40% to approximately 28% in that period, a stunning reversal. What caused this sudden fall? Part of it was Nikon being late to a critical innovation: immersion lithography. When the first high-volume immersion scanners came out around 2005 to 2006, using water to improve the lens resolution for 65 nanometers, 45 nanometers nodes, ASML jumped ahead. In 2006, the first year of immersion tools, ASML grabbed about 72% of the market, while Nikon had 28%. Canon didn't even participate at that high end. ASML simply executed better on the new tech. Their immersion scanners had higher throughput and quickly became the standard for leading-edge fabs. Nikon's response was slower, and it never caught up in immersion performance. By 2011, ASML held 82% of the immersion market versus Nikon's 18%. Once you lose on a key generation like that, it's hard to regain ground. The best customers stick with the supplier that's ahead. The EUV gamble sealed the deal. Nikon actually shipped one experimental EUV tool in 2008, beating ASML to that milestone. But Nikon paused after that, citing technical challenges, and announced that a production-ready EUV scanner would be ready only by 2014 to 2015. That proved far too optimistic, or perhaps a tacit admission of delay. Meanwhile, ASML forged ahead. By 2011, ASML had shipped 3 early EUV machines to research customers, and critically, it kept investing billions, with the help of partners like Intel, Samsung, and TSMC, who literally bought stakes in ASML to fund EUV R&D. Nikon, by contrast, effectively bowed out of the EUV race in the 2010s as the costs escalated. As one industry commentator noted in 2017, ASML achieved a 100% monopoly in EUV and over 90% share in immersion DUV. Nikon was essentially out of the running for the leading-edge lithography business. That same year, Nikon pursued a last-ditch legal battle, suing ASML and its lens supplier Zeiss for patent infringement. It was a desperate move. The two companies had sued each other back in 2001 to 2002 as well, and many saw it as Nikon's final capitulation in high-end lithography. After all, suing your rival isn't a growth strategy. It was a way to seek compensation as Nikon's own R&D sputtered. By the late 2010s, Nikon and Canon had been relegated to the sidelines. They hadn't fallen completely silent. Far from it. Both companies still retained profitable niches. They left the center stage of the high-end market, but never stopped exploring lithography technology. In practice, that meant focusing on less bleeding-edge, but still important, segments. KRF and I-line steppers, which use longer wavelengths for mature 90 nanometers and above nodes, are still used in huge volumes for things like sensors, power chips, MEMS, and displays. Canon and Nikon continued to occupy a large share of these mid- and low-end markets. For example, Canon led the market for I-line steppers in the 2010s, and Nikon maintained a solid share as well. These tools are cheaper, a $5 million I-line tool versus tens of millions for immersion, but they sell in volume. Canon, in fact, pivoted heavily to those legacy markets after 2002 and dominated them. Nikon stayed in as well, but struggled to differentiate itself for a while. Another quiet stronghold for the Japanese duo was flat panel display FPD lithography. Nikon and Canon essentially monopolized the market for lithography equipment used to produce LCD and OLED panels for TVs, smartphones, etc. These FPD tools are huge. They project patterns on glass substrates larger than a meter, and they leverage the same core expertise in optics and mechanics. While not as high profile as silicon lithography, FPD lithography has been a steady business and kept Nikon's precision equipment division alive through the 2010s. So Nikon wasn't dead, but it was licking its wounds. Its semiconductor equipment revenue in the late 2010s was a fraction of ASML's. For instance, in 2022, ASML's revenue was about 21 billion euros, whereas Nikon's precision equipment business, including FPD and semiconductor lithography, was on the order of 295 billion yen, approximately $2.5 billion. Nikon went through restructuring, cutting costs, and refocusing on areas where it could still win. The company also started looking for high-margin niches where ASML wasn't playing. If Nikon couldn't win the EUV game, it needed to change the game. This realization set the stage for Nikon's mid-2020s strategy, to pivot from chasing the absolute cutting edge to innovating in adjacent, underserved domains of the semiconductor manufacturing process. By 2025, Nikon's plan had crystallized into two main weapons for its counterattack. 1. Advanced packaging, and 2. Nanoimprint lithography. Each of these takes advantage of Nikon's strengths, precision optics, large area lithography know-how, and metrology expertise, while sidestepping direct competition with ASML's EUV juggernaut. It's the classic flanking strategy. Attack where your opponent isn't expecting it. Next, we'll explore each of these two fronts in detail and see how they might redefine the lithography wars. Modern high-performance chips aren't just single slabs of silicon anymore. Chiplets have become the trend for CPUs, GPUs, and AI accelerators. Instead of one monolithic die, which is harder to manufacture without defects, companies like AMD and Intel are designing processors as multiple smaller dies that work together in one package. Think of it like Lego blocks. You take several chiplets, CPU cores, memory tiles, I/O tiles, etc., and connect them on a substrate to act as one chip. This modular approach improves yield, smaller dies equals less chance of defects, and allows mixing different technologies. For example, logic chiplets on cutting-edge nodes can be paired with memory or analog chiplets on older nodes. The result is better performance at lower cost, but only if you can package those chiplets together with extreme precision and tiny interconnections. This is where advanced packaging comes in. Technologies such as 2.5D interposers, fan-out wafer-level packaging, and 3D stacking, like TSMC's CoWoS or Intel's Foveros, are enabling tens of billions of transistors from separate dies to communicate as one. The kicker is that, as packaging becomes more advanced, it starts to look a bit like another layer of lithography. To wire chiplets together, you often need to create high-density interconnects on an interposer or substrate, essentially tiny wiring layers with micron-scale features. Traditionally, packaging has used older lithography, like eye-line steppers or contact printers for solder bumps, which might print features tens of microns wide. But chiplet architectures now demand much finer patterning, down to a few microns or even sub-micron in the most aggressive roadmaps. In addition, the packages are growing in size. A multi-chip module can be much larger than a single die wafer area. Some advanced packages use panel-sized substrates made of glass or organic material, bigger than the traditional 300mm 12-inch wafers. All this drives the need for new types of lithography tools tailored to back-end packaging. Enter Nikon's DSP-100 digital lithography system, the company's newly announced weapon for advanced packaging. In July 2025, Nikon began taking orders for this machine, which is designed specifically for back-end packaging processes. It's a radically different beast from a classic wafer stepper. First, it supports large substrates up to 600mm by 600mm, essentially panel-level packaging instead of wafer-level. This means a substrate 9 times the area of a 300mm wafer can be patterned in one go, greatly increasing throughput for big chiplet interposers or multi-chip panels. Second, it offers high resolution of 1.0 micrometer line and space, with exceptionally fine alignment accuracy, overlay error less than plus or minus 0.3 micrometer. Those specs are an order of magnitude better than old-school packaging lithography. Nikon achieved this by combining its semiconductor lithography know-how with its flat panel display FPD technology. Specifically, the DSP-100 uses multi-lens projection modules arrayed across a wide field, Nikon's proprietary method from big LCD scanners, to expose a large area with uniform quality as if it had one giant lens. This tackles a key challenge. Covering a 600mm substrate with sub-micron precision is impossible with a single lens, so Nikon uses many smaller lens systems in tandem. The second prong of Nikon's strategy is a bit more speculative, but potentially even more disruptive: nanoimprint lithography. Here, we must note, Canon has taken the clear lead on this front, surprisingly making Canon a kind of ally in mission to Nikon, though they are competitors. The central idea is to challenge the dominance of EUV in making the most advanced chips by using a completely different technique that's cheaper and simpler. Think of it as the guerrilla warfare approach to lithography. Instead of building ever more complex and expensive machines, the way EUV has, try a radically simpler method to achieve similar results. Canon's development in NIL is instructive. In October 2023, Canon announced the FPA-1200NZ2C nanoimprint lithography system, claiming it can pattern down to 14 nanometer features, equivalent to the 5 nanometer node used in cutting-edge logic fabs. Canon even projects that with further improvement, NIL could reach 10 nanometer patterns, roughly the 2 nanometer node. Instead of using a reduction lens and light, this machine literally presses a quartz template with circuit patterns into the photoresist on the wafer. It's like stamping a wax seal, but at nanoscale precision. Each imprint can copy an entire layer's pattern in one shot. Canon has worked on this tech for years, acquiring Molecular Imprints Inc. in 2014 to get core NIL IP, and partnering with Kioxia, a major flash memory manufacturer, to refine it for actual chip production. By 2024, Canon's NIL tool was delivered to a research consortium in the US, Tech Insight, TIE in Texas, that includes Intel, Samsung, and others, for evaluation. This indicates that even the big players are curious. Could NIL supplement or even replace some EUV steps? The promised advantages of NIL are eye-popping. Because the tool doesn't require a high-energy light source or expensive optics, it's far cheaper and uses far less power. Canon's CEO, Fujio Mitarai, said the price of a nanoimprint tool could be an order of magnitude lower than an EUV scanner. Even if that is optimistic, data from Kioxia's trials shows NIL equipment might cost about 40% of an EUV system and consume only approximately 10% of the power. To put that in concrete terms, if an EUV tool costs approximately $150 million and draws 1 megawatt of power, a nanoimprint might cost approximately $60 million and draw 100 kilowatts while operating. Those are huge reductions. For chipmakers, this means a potential path to reduce the astronomical capital and operating costs of leading-edge fabs. NIL tools also have a simpler bill of materials, no need for ultra-pure tin droplets and plasma lasers, or $30 million reflective mirrors. Maintenance could be easier in principle. There are also technical merits. NIL isn't limited by the optical diffraction limit in the way light-based lithography is. In theory, the resolution of imprint is down to the capability of making the master template, which can be done with e-beam lithography at sub-10 nanometers. NIL can also do things like imprinting 3D structures or novel patterns that are hard to achieve with multi-patterning. For example, Canon and Kioxia have suggested NIL could be great for making advanced memory devices, NAND flash and DRAM, where you have very regular patterns and multiple layers. Memory manufacturing often repeats identical patterns millions of times. Think of a NAND flash's cell array. A stamp technique could imprint a whole wafer's worth of memory cells in one go very efficiently. Kioxia reported that NIL could slash energy use and equipment costs in memory production significantly. It's easy to see why smaller or budget-conscious chipmakers might be excited. NIL could lower the barrier to entry for making sub-10 nanometer chips, which until now basically required buying a fleet of EUV tools, multi-billion-dollar proposition.